Here is problem 1126. The 1,560 kilogram solid steel door to a bank vault is 2 meters high, 1 meter wide, and 10 centimeters thick. One hinge is 60 centimeters down from the top of the left-hand side of the door. The other hinge is 30 centimeters up from the bottom. What horizontal force and what direction does the door exert on the upper hinge? Let's take a look at this situation. We've got ourselves a door, rectangular door. It's 1 meter wide and 2 meters high, and it's 10 centimeters thick. That's really not going to matter much because we're going to be looking at this in the two-dimensional sense in the XY plane, so the thickness is not going to matter. We have a hinge that's 0.6 meters down from the top, and another hinge is 0.3 meters up from the bottom. If I can get this to right. So there's a distance of 1.1 meters between these two hinges. And we're going to have a center of mass right in the center of this rectangle, and from there is the force of gravity, mg, bearing down like this. So we're going to label our lower hinge A and our upper hinge B. Now there will be forces acting at both of these places, reaction forces. Now we're going to be interested in the force at B, so let's do our torque about point A, because if we do that, we can eliminate the forces that go through A from torque consideration. Hence we only need to concern ourselves with the forces acting at B. There's some kind of reaction force which will have a vertical component and a horizontal component, which could be going to the right or to the left. Now my intuition says it's going to the left because I'm going to need a torque to balance out that mg torque. So I'm going to go that way. But if I had gone to the right, I probably would end up with a negative value for that force, which is fine. It just means that I assumed the wrong direction for the horizontal force. Okay, so the line of action for this weight force is this line right here, vertical line, giving me a moment arm for that weight force of 0.5 meter. So that's 0.5 meters for that moment arm. And the line of action for the vertical component of the reaction force at B is actually this vertical line. It's got no moment arm about point A, and hence the vertical component is going to be insignificant in terms of torque. It's radial torque about point A. The line of action for the horizontal force is this one right here, and that will have a moment arm of the 1.1 meters. So, and that's the way we're looking at it. Let's redraw this in terms of a torque diagram. So here's my point A, and 0.5 meters away I've got the gravity force. So even though gravity is acting at the center of mass, we want the shortest distance to its line of action, which is 0.5 meters. And that torque is trying to make this thing go in a clockwise sense, which would be a negative torque. And then I've got this horizontal component up here at a distance of 1.1 meters. And that thing is trying to make this thing go counterclockwise about point A. And that would be a positive torque. So these two torques are balancing out so that we have no net torque about point A. So the summation of all the torques about A is 0. That's equal to 1.1 times H minus 0.5 times mg. Solving this for H, we have H is equal to 0.5 mg over 1.1, which is going to equal 0.5 times the mass, 1560, times 9.8 over 1.1, and that's equal to 6,949 newtons. Positive value, so our assumed direction is correct. It's going to the left at that point, the horizontal force. So on the upper hinge, we have a force of 6,949 newtons to the left on that upper hinge.